on it.
Okay, got that going. Today we're basically going to be covering stuff that we've already happened to talk about in calculus. And so I think it'll be a pretty easy one. So first off, well, I don't know if we technically defined displacement yet. I'll be right on the board. But reminder, difference between displacement and distance. Right? If I start out right here, and I walk this way a meter, turn around and walk back, my total displacement is 0. I'm back where I started. Displacement is final position minus initial position.
Yeah.
My distance, on the other hand, was 2 meters. Make sense?
Mm-hmm.
So distance versus displacement. So then we also have average velocity versus average speed. Once again, if I walk 1 meter per second this way for 1 second, and then 1 meter per second this way for 1 second, what was my average speed?
1 meter per second.
1 meter per second. But what was my average velocity? 0. I'm back where I started.
Yeah.
Make sense? So quickly, our definition for average velocity then is your final position minus your initial position, maybe x1 minus x0, all over the time interval that takes you to do that. Try and follow his subscripts here. They see the exact same definitions. So your final position minus your initial position divided by the time you were at your final position minus the time you were at your initial position. If I was here at exactly 3 o'clock, here at 3 o'clock in 1 second, here at 3 o'clock in 2 seconds, my displacement was 2 seconds. So that difference would be 2 seconds. Make sense?
Yeah.
And then some notation you're already familiar with. This is the same thing as delta x over delta t. Our change in x over our change in time. Right? Mm-hmm. And then, how do we define instantaneous velocity then? Instantaneous velocity is the limit as delta t goes to 0 of delta x over delta t, which we already know is dx dt.
It's the derivative?
Whoa, I thought we already knew this.
Well,
Velocity is derivative of position.
Because you take the s.
of position, yeah.
Oh yeah, you guys were used to seeing s's. Okay. The way that we were using s's in calculus, I'm now using x here. Sorry. X is your position.
Okay. Yeah, that makes sense now.
Okay, makes perfect sense.
Mm-hmm.
And then similarly, your average acceleration is your change in velocity divided by your change in time.
Okay.
Question?
Go ahead.
Never mind.
Got it?
Yeah.
So if I was going 10 meters per second, and a second later I'm going 20 meters per second, I accelerated 10 meters per second squared.
Per second squared.
Oh yeah, let's think about the units of these really quick. So average velocity, notice the units up here. Delta x is what?
Position.
What's the units on that?
What do you mean, what's the units in that?
It's just meters.
It's a distance, or
Well, it's your
displacement is in
position.
meters. It's a change in position.
Oh, with yeah,
Delta is
with
your
t,
change in position.
with delta t, not just delta x.
Ignore that for a second. Delta x is your final position minus your initial position. If
Oh.
my final position is at 20 meters, and my initial position is at 10 meters, delta x is equal to 10 meters.
Okay.
Okay, so the units up here are meters. What's the units down here?
Just seconds.
Seconds. So your velocities are meters per second.
Okay.
Make sense?
Yeah.
Okay. So, let me write out the same thing down here. So change in velocity over change in time. We can also write that as delta v over delta t. This is going to be, what's velocity? We just barely figured out the units of velocity. That's meters per second. But now, over time is seconds.
And that's how you get your
So
square.
this is the same thing as meters per second squared.
Okay.
So sometimes people say meters per second per second. You're changing meters per second, per second.
I see.
Yeah.
So a lot of times we say it that way because that appeals to our intuition more than meters per second squared. We're like, how's that acceleration? It makes no sense. But when you think about it this way, it makes more sense. But we'll always say meters per second squared because it's easier. Okay, so now we talk about instantaneous acceleration. How do we define instantaneous acceleration? Exactly as you expect. It's the limit as delta t goes to 0 of delta v over delta t, which is equal to dv dt, which is equal to the second derivative of x with respect to time.
Yeah.
Squared. All the same thing, right?
Okay.
Now, geometric interpretation. We may already remember this, but in case you forgot some of it, let's remind you really quick. So this right here is my x-axis, don't get confused. Your position, your x-axis. This right here is the time axis. So I'm plotting your position at a time.
Okay.
So maybe you start out here, and maybe you start by speeding up, running forward, then you come back, turn around, run back, and end up back where you started. You with me?
Mm-hmm.
So some sort of complex motion here. Now notice that you're picking up velocity, picking up velocity. So here your velocity is positive, right? You're speeding up, you're going that way. Velocity, remember, we can interpret as geometrically as a slope. The steeper the slope, the more your velocity, the shallower the slope, the less your velocity. Here your velocity is 0. And then here your velocity is negative because you turn around and they're coming back. So this is straight line motion. Don't get confused by what this motion is. This motion looks something like I run this way, I stop, turn around, I go back further than where I started, and then come back and end up where I started. This is straight line motion.
Okay.
It's the motion with time. It's just going up, then down, then back up. And we're just plotting it at each instant of time where it was.
Okay.
That makes sense?
Mm-hmm.
Okay. So the slope gives you your velocity. Your acceleration is determined by, do we remember?
The weird.
Concavity.
Yep.
Yeah, you got the right idea. Concavity. Remember, where we're concave up, or where it looks like a smiley face, it's concave up. Where it looks like a frowny face, it's concave down.
Mm-hmm.
If it's concave up, that means we have positive acceleration. If it's concave down, that means we have negative acceleration. So you're speeding up, speeding up, speeding up, speeding up, speeding up. And then here you're slowing down, slowing down. You're still moving forward, but you're just slowing down, slowing down, slowing down, slowing down, come to stop.
Okay.
And now you're slowing down even more, meaning you're moving backwards. So you're speeding up, if you just think about it as your speed, but your velocity is becoming more and more negative here.
But your acceleration is speeding up.
Acceleration has a direction just like velocity. If your velocity is becoming more negative, your acceleration is negative. So we shouldn't say speeding up and slowing down, let's not say that. We'll say velocity becoming more positive or more negative. So a really negative velocity is going that way really fast. A really positive velocity is going that way really fast.
Okay.
So here, your velocity is 0. Then your velocity is becoming more positive, more positive, more positive, more positive, more positive. So now it's a big number, like 10 meters per second. And then it's becoming more negative, more negative, more negative, more negative, more negative. By the time you get here, it's like 0 meters per second. And it's becoming even more negative, more negative, more negative, more negative. And by the time you're here, it's like negative 10 meters per second. And now it's becoming more positive, more positive, more positive, more positive. Here it's back to 0 meters per second. And more positive, more positive. Does that make sense?
Yeah.
Can you kind of visualize what's going on with this particle? Because going through these graphs to like a physical understanding of the graphs is going to be extremely useful. And vice versa. Going from some physical understanding to being able to represent on a graph.
Okay.
So your slopes are your velocities. Your concavity is your acceleration when you're talking about a position function. Right?
Okay.
That's only when you're talking about position function. If I were to plot a velocity function, now I'd have to integrate to get my position, and its slope would be the acceleration. Let's look at one super simple example of that one. You with me? So now I am going to plot your velocity with respect to time. It's more rare that we do this. We typically do position, but I just want you to see how the calculus integrates with the physical concepts. So here we have our velocity, what's it called? Axis. And here we have our time axis. Okay? Now I'm going to assume that you are just, we'll start with stupid simple and then we'll get a little bit more complex. Stupid simple. You are moving with a constant speed. We'll put actual numbers on here to help us do some math. So this is 2 meters per second. You're moving at a constant speed of 2 meters per second for 10 seconds. Question, how far did you go?
To 20 meters.
Yeah, if I'm going 2 meters per second, and I do that for 10 seconds, I go 20 meters, which is the exact area right here.
Okay.
Because it's like, since the height is your velocity, it's like how much distance you travel in that little interval of time. This little interval of time, this area, gives you the little distance you traveled.
Mm-hmm.
And that's true all the way across. So it's an integral. Make sense? Now I'll do one, sorry, I forgot to ask you another question. If my acceleration, or if my velocity is always 2, what's my acceleration? 0. I'm not accelerating. I'm maintaining my same velocity.
Yeah.
What's the slope of that line?
0.
0.
Okay.
Maybe that simple example was enough for you to see the connections.
Yeah.
Okay, so when we plot velocity, the integral gives us position, and the derivative gives us acceleration, which we already do, right? Because I know if I have acceleration, the integral is velocity, and the integral of that is position.
Yep.
Because this is the derivative of position, this is the derivative of velocity. So you can go back and forth between these equations. It's important to understand that connection, both geometrically and, we'll say, calculusly.
Calculus.
Realizing how they're connected by derivatives and integrals. So no questions on any of that, right?
Yeah.
Good? Okay. So I think we got through a bunch of our basic definitions. I think I want to do all my derivations before I go back and start doing example problems. So now we're going to derive what are called they're often referred to as the 4 kinematic equations. This chapter, I should have introduced the chapter a little bit better. What are we doing in this chapter? In this chapter we're doing one-dimensional motion along a straight line. Motion along a straight line, one-dimensional motion. Another way you might say is one-dimensional kinematics. So in the beginning of the class, we're talking about kinematics, and then we're going to introduce what we call dynamics. Kinematics is where you determine the state of the system, or you determine how the system's going to change simply by knowing the state of the system. You don't know any of the forces involved. There's the easiest way to say it. I don't talk about the force of gravity on this. We haven't done any examples yet, so that might not make sense. You're going to describe something like a marker being thrown through the air.
Okay.
And the way that you're going to describe that is by knowing its acceleration downwards, and its initial velocity, and its initial position. So by knowing its position, velocity, and acceleration, you'll describe how it moves through the air. And we're never actually going to talk about the force of gravity on it.
Because that's in the acceleration.
It happens to be accounted for in the acceleration, but when you don't use forces to describe when you talk about how forces change a system, that's called dynamics. When you ignore the forces, and you just talk about basically their effects, like it's accelerating, if gravity's accelerating downwards, and we just use acceleration, it's called kinematics. It's just terminology. It'll make more sense. Once we finish dynamics, maybe I'll go back and explain the difference. Once you actually have something to contrast.
Okay.
Shouldn't have gone down that road. Bad idea. Anyways, so we're going to, I was just trying to help you understand why they're called the kinematic equations. We're going to derive the 4 kinematic equations now, is what they're often referred to. And they're the equations that you will use a lot for the first few chapters in this book to describe the motion of things. Okay? And in particularly, we're going to be interested in motion when acceleration is a constant. So the 4 kinematics apply when acceleration is a constant. Now, why would we derive these equations for when acceleration is a constant? Do you have any inkling why we're so interested in that special case when acceleration is a constant?
When acceleration is a constant.
Yes.
You can derive it when it just be 0.
When it's a constant. So let's go back and have a quick discussion about Galileo Galilei. What did he do? And this will get us thinking about science once again. and how science works. So there he is, Galileo in his lab. Not exactly what he was doing, but gives you the idea. And he was measuring how things fall, and he was measuring their acceleration.
Okay.
So he dropped something, measure its acceleration. You say, okay, that time it looked like it accelerated at 9.82 meters per second squared. And then he does it again. And the next time he gets something like 9.8. And he does it again, maybe 9.81, does it again. Maybe next time he gets 9.78. And he's doing it with a bunch of different objects. So one time he drops a bowling ball, the next time he drops a marble. He's dropped a lot of things, measuring how they fall. And he comes to this conclusion, oh my goodness. All objects accelerate downwards. Acceleration is always 9.8, I think is the number we'll use in this class, meters per second squared, no matter what you're dropping. Okay? Hopefully that's already intuitive to us.
Yep.
I don't know if you've come across that before. Trying to find something heavy I can drop in here. Probably drop my textbook fine. We got a textbook and a marker. If I drop them both on the floor, which one's going to hit the ground first?
Well, it depends on your position and
Roughly speaking. Will it hit the ground at the same time, or will this hit the ground first, or will this hit the ground first?
they'll both hit the ground at the same time.
They'll both hit the ground at the same time. Heavier objects don't fall faster. Why not?
Why not?
Why not? It's obviously being pulled to the earth harder. I can feel it. Why doesn't the heavier object fall faster? So we'll come back to that question, but for the time being, surprising fact that Galileo discovers is all objects accelerate downwards at 9.8 meters per second squared. You with me?
Yeah.
Now, we use this number so much that we also call it G. And if we want to call down the negative direction, we need to say negative.
It's like gravity.
Like gravity. It's a force of gravity. So A is equal to negative G. And you have 9.8 meters per second squared. It's constant.
This is one of our kinematic equations.
No, this is a special case of them. So we're going to create kinematic equations for when acceleration is any constant. But Galileo figured out that acceleration when we're dropping objects on the surface of the earth is exactly this constant.
9.8 meters per second squared. Okay.
Yes. So, since we're going to be doing a lot of physics and solving a lot of problems that have to do with you throwing objects on the surface of the earth, we're very interested in the case where acceleration is a constant.
I see.
You with me? Mm-hmm. So, now resetting, we're not going to say acceleration is this specific constant. We're just going to say, let's go back and say that acceleration is some constant, any constant.
Okay.
And I'm just going to rewrite it as A, so that when it shows up in later equations, remember that A is the acceleration, rather than something like C. You with me?
Yeah.
Okay. So now, if acceleration is a constant, what is velocity?
It's nothing.
Plus C. VT plus C.
Acceleration. So, now that we missed half the lecture on the camera, let's jump now a little bit into chapter 3. We'll review all this again next week, most likely, but just get you comfortable with notation now.
Okay.
Okay, so now how are we going to represent position? And we're going to use three-dimensional vectors most of the time, since it's easy to go from 3 dimensions to 2 dimensions. The inverse isn't necessarily the case. So how do we represent position now? What does our position function look like? We use R for position. We're going to represent your position as a vector now, not a point.
Okay.
And that is going to be equal to, we're going to do x times I hat plus y j hat plus z k hat. And this way you can still think about x gives you your x position, y gives you your y position, and z gives you your z position, exactly how you know and love.
Why
Okay.
is it an R?
Well, what else are we going to call it? We're using x here, y here, z here.
True.
So it's an R. So that's how we're going to represent your position with a vector now.
Okay.
Good?
Mm-hmm.
Now your average velocity vector is now going to be equal to the change in your position vector. So you can write it as R2 minus R1. Over time is still just a scalar.
So it's
So it's
just
still just T2 minus T1. And those are just scalars, not vectors. You don't represent time as a vector, it's just a scalar. Remember, scalars are just numbers. So some quantities we need vectors to represent, some we just need numbers to represent. And you'll notice that this is the exact same equation as like what we had before. Another way that we can write this, we can say that this is delta r vector over delta t. Right?
Okay.
And once again, if we want your now your velocity vector, or your instantaneous velocity, that is going to be the limit as delta t approaches 0 of delta r vector over delta t, which is going to be equal to the derivative of your r vector with respect to t.
Do derivatives
Okay.
work the same with vectors?
Yes, so quick cap on how you take the derivative of a vector. So your position vector might look something like, we'll say, not x, your position is going to be determined by your time, right?
Yeah.
So maybe your x position is 2t, plus maybe your y position is 5t squared, and maybe your z position is just 10. So you're staying at constant height. So you're staying at constant height of 10. We'll say that this way is your z, so we'll say x, y, z. You with me?
Mm-hmm.
So this motion roughly looks like you're staying at 10 in the x direction, so that's that way. Every second you're going 2 meters, but at the same time in the y direction you're following this path, so you're shooting off in the y as you go out. Does that make sense?
So you're going up a bit. Well,
You're not going up. Your height's staying the same. Y is that way, x is that way. So you're moving in the x direction 2 meters every second.
Mm-hmm.
And while you're doing that, you're moving in the y direction. In the first second, you're going to go 5 meters. In the second you're going to have gone 20 meters.
Okay.
So you're making like this parabola looking thing.
So it's just like what it looks like in the second dimension, just at the 10.
Just at a height of 10. Yeah,
Okay.
I intentionally made the z constant. So if we think about the z coming out, should have just drawn it in the whiteboard. If we think about the z coming out of the whiteboard now, and then we'll call that your x, that your y, then it's going to look like this. Here's roughly what the position is going to look like. Something like that. More parabolic than that. Something more like this. Where this is your x, that's your y.
Oh,
and
you're
it's
saying the
coming out.
whiteboard is 10.
Yeah, and whiteboard is at z equal to 10.
Gotcha.
So it looks something like that. That's your position vector. Anyways, so what would your velocity vector then look like? So your velocity vector then, which we know is the derivative of your position vector, is just going to be equal to, you just take the derivative of each of the components. So it's just going to be 2i hat plus 10tj hat plus nothing, 0k hat.
Okay.
So you only have velocity in the x and y direction. You don't have any velocity in the z direction.
Gotcha.
But it's important that you keep a 0 there, because if we also write this vector differently, we could also write this as 2, 10t, 0. Keep the 0 there so that you remember it's a 3-dimensional vector. It's not a 2-dimensional vector.
Oh, I see.
Make sense?
Mm-hmm.
Yeah.
Okay.
So
So-
J hats and J hats and I hats don't do anything except keep going with the.
It's just another way of representing it. The I hat, j hat, and k hat, those represent unit vectors. Remember?
Yep.
Okay. So similarly, now your average acceleration vector is going to look exactly like what you expect it to. It's going to be a v2 vector minus a v1 vector all over t2 minus t1, or it's going to be equal to your change in your vector, or in your velocity over your change in time. And your acceleration vector is going to be exactly what you expect. It's going to be the limit as delta t approaches 0 of your change in your velocity vectors over your change in time, which is going to be the same thing as dv dt, which is the same thing as the second derivative of your position vector with respect to time. Almost identical, just weirder, more confusing looking notation.
So why do vectors act the same way as like normal derivatives and integrals? Like how can you derivate a
Because you can
vector?
focus on just one thing at a time. So a vector accounts for all 3 dimensions of this thing's movement, right?
Yeah.
But if you want, you can just focus on its movement in the x direction. And you can talk about speed in the x direction. And then you can focus on its movement in the y direction and talk about speed in the y direction, and focus on its movement in the z direction and talk about speed in the z direction. So you can talk about one direction at a time. Which is why when you focus on just one component, you can still just take its derivatives and integrate the way you know, love, and have always done.
Yeah, that makes sense.
So anyways, now we have shorthand for talking about components of these things. Because when I represent r vector, another way I might write my r vector is the way we typically talk about, it's going to be an x, a y, and a z, right?
Mm-hmm.
So anytime you see x equals, it's understood now that you're talking about the x coordinate, or that you're talking about the x component of your position vector.
Always.
You can infer from context, typically.
So if it's talking about vectors.
If it's talking about vectors and you see an x pops out there and you're like, where'd my x come from? They're talking about this.
Okay.
Similarly, your velocity vector now, we'll talk about it in terms of, we'll do v sub x for this component, v sub y for this component, and v sub z for this component. So if out of the blue you see a v sub x, they're talking about the x component of your velocity.
Okay.
Similarly, with acceleration, you'll see similar type stuff.
Why don't they do like r sub x and r sub y?
Because it's already x, y, z the way you know and love and are used to working with it. This x now functions exactly how you've always treated x.
Because it's position. That makes sense.
Because it's just your x position.
Okay.
You're just grouping your x position, y position, z position all together in one thing called vector. Because we can do nice math with vectors.
Okay.
Okay, so this is the way you represent. You'll see this notation just pop out of the blue. When that notation pops out of the blue, that's the reason why. And so, really quick, rewriting these kinematic equations now, the way that they're written in your book, and not the way I have them written here. Here's how they show up in your book. And now you'll make sense of why they wrote this in your book. And all they do is add subscripts in there like that to make it clear that these equations happen to have been describing everything in the x direction.
Okay.
We could have also done the same thing for describing motion in the y direction, and could have also done the same thing for describing motion in the z direction. So if I were dealing with some acceleration vector, and it turns out that the ax were a constant, then I know that these all hold. And if I found out that the ay was a constant, then I know that these all hold when I replace all my x's with y's.
Yeah.
And if similarly, if this were a constant, then I know that these all hold when I replace my x's with z's. That make sense?
Mm-hmm.
Okay. Yeah, it's pretty straightforward. It's just a lot of notation, and it's easy to drown in the notation a little bit. So, write some more stuff that is probably already obvious to you from how I have things written here, but we're just going to write it explicitly just to make sure you see it. So Vx here now, Vx is the same thing as the derivative of x with respect to t.
Yeah.
This is a derivative of this component. So it's still dx dt. Similarly, dy is dy dt, and dz is equal to dz dt, and similarly, a sub x is equal to dvx dt, ay is equal to dvy dt, and az is equal to dvz dt. And hopefully that's all pretty straightforward and makes sense.
Yep.
Again, just a ton of notation. Okay. So, see how we're doing on our camera. Seem to be doing fine. So let's just try an example problem now, hopefully using some of this notation, just to help cement it in, I guess. So a robotic vehicle, or a rover, is exploring the surface of Mars. The stationary Mars lander is the origin of the coordinates. And the surrounding Martian surface lies in the xy plane. The rover, which we represent as a point, has x and y coordinates that vary with time. X is equal to that, y is equal to that. Maybe I'll intentionally use this notation even though the problem doesn't, just to try and help cement it in your head. So we've got a rover moving on the Martian surface, and its position vector, now we're only talking about in 2 dimensions.
Okay.
Its position vector is equal to, and maybe I'll write it this way, it's equal to 2 minus 0.25 t squared and 1 plus 0, 1 plus 0.025 t cubed. So this is how its x position is changing, this is how its y position is changing.
Okay.
With me?
Is changing or?
This gives you the x position at any time, this gives you the y position at any time. And they have a rough plot of how this thing's moving. Or maybe we're supposed to make that plot. Let's just find it. Find the rover's coordinates and distance from the lander at t equal 2. Find the rover and displacement and average velocity vectors for the interval t equals 0 to t equal 2. Find a general expression for the velocity. Okay, so really quick, let's first just write the velocity vector. I know that's the last thing we're supposed to do, but let's do that one first. What's the velocity vector then going to be?
It's just 2 times 0.25t. So what is that, 0.5?
Don't forget your minus.
So negative 0.5?
Negative 0.5 t squared, or t, right?
Yeah.
Just taking the derivative of this, comma, and then the derivative of this one. Just that, right?
Yeah.
Okay, so there's our velocity vector, here's our position vector. So this can give us our velocity in the x direction at any time, our velocity in the y direction at any time, and this gives us our position, our x position at any time, and our y position at any time.
Okay.
Okay? So, first thing we were supposed to do is find the rover's coordinates and distance from the lander at time t equal 2. So our lander is somewhere over here, and our rover is somewhere over here. At t equal 2, we're going to find out where it is, and then find its distance to the lander.
So displacement?
Yeah.
Okay.
Okay, so at t equal 2, what is the position of this thing? So at R2, at 2, we just plug 2 into that equation, right?
Yep.
So we have, well, probably don't even need it. 2 squared is 4, 4 times 0.25 is 1, so 2 minus 1 is 1. And then on the next one,
8 times that.
we have,
This is
0.2, so 1.2, I think.
yeah.
When we plug in 8 times that, that's 0.2, right? Is that what we said?
Yep.
Yeah, 1.2.
So then we have 1.2. Okay, so see if that's the same thing that they got. Time 2. What was the distance? Find the rover's coordinates and distance from the lander at time equal 2. So at time equal 2, let's just put some tick marks on here. 1, 2, 1, 2. Okay, so we're at 1 and 1.2. We're up here. Right?
Yep.
So our position vector looks like this. Oops. It goes from our origin, which is our lander, and it points to that point. So it's pointing to our current position.
Okay.
Let's plot another couple points just to get a feel for the scene. What happens when we plug 0 into the sink?
You just get 2.
You just get 2, comma.
1.
1.
So R at 0 is equal to 2, comma 1. So 2, comma 1, so that was right here. Right, and so the position vector is the vector that points there. It's this vector.
But doesn't he start
So
off?
the path,
I'm confused.
no, he didn't start here.
Oh, so at 0 seconds he was there.
The rover is just somewhere out here,
Okay.
and it's just chugging along. So here it is at 0 seconds, and it's just chugging along, and in that time, it somehow goes over there. And then, I'm not sure what goes in between.
So what's the origin point?
The origin is where our lander is.
Mm-hmm.
Oh.
I'm wondering if I set up something weird, because we don't have the same pictures in. Yes, I did. Some again. It's because they put so much junk with their units in there, it's hard to read exactly what it is. So they have 1 T, so T, and then that plus or minus. T plus 0 point blah blah blah. Okay, so we messed up. So when we take the derivative here, now this is going to be 1 plus 0.075
G squared.
t squared. Okay, so that was our mistake. That's why the picture's not the same. So let's see, one more time. When we plug 0 into here, we just get 2. So 2, 0. And when we plug 2 into here, what do we get? This one still stays the same. We get 2.2, right?
2.2, yeah.
Or 1.2. Or 1 and 2.2,
Yeah.
sorry. Okay.
Why is it- Didn't you plug another?
So let's redraw that picture.
Yeah, that's right.
So let's see. 2, 0. So that position vector is right there. And then we have 1, 2.2. That position's right there. Okay, that looks more like it. Let's really quick do 1 on there. R1, just to see where that is. When we do 1 on there,
1.75.
we get 1.75. So. And then what do we get on the other one?
2.025.
2.
1.
1.025.
Oh, yeah.
So we're 1.75 this way, and then basically 1 this way. So I'll give you a sense of the path this thing takes.
Okay.
Now the point we were interested in was right here. So here's our position vector, the vector that points to our position.
Mm-hmm.
And now I can't remember what we were actually trying to do.
Just
A, find the rover's coordinates and distance from the lander at time equal 2. Okay, distance. Distance from here to here is just the magnitude of this vector.
Magnitude.
The length.
That's right.
Magnitude. So the magnitude of R2 is equal to the square root of the sums of the squares of its components, of that squared plus that squared.
Yeah.
Of 1 squared plus 2.2 squared, which is equal to
root of 5.4 squared.
second square root of 1 plus 2.2 squared is equal to, can't remember how many significant figures we had, so for now I'll just write 1.45. sanity check. I hit the divide button instead of the exponent button. 2.42.
Yeah.
That makes way more sense. Because, yeah, it definitely has to be more than 2. Good check. Okay, so that's its position vector. That's its displacement from the origin. Let's see, what else do they want? B, find the rover's displacement and average velocity vectors over the interval t equals 0 and t equal 2. So t equals 0 and t equal 2. So I need, we already have r at 0, we already have r at 2. I'm looking for its displacement. Sorry, let me read that one more time. Find the rover's displacement and average velocity vectors. So its displacement is, so we're looking for delta r hat across 1 and 1, 2. So we'll figure that one out. And then the next thing we also have is part B, average velocity over the interval. So then we're also looking for V average over that interval. So displacement, that's our ending vector minus our beginning vector.
Okay.
Right? So I'm doing this vector minus this vector.
The other vector on top, yeah.
So 1 minus 1.75 is negative
Aren't you
0.75.
beginning at R0?
Oh, thank you. Those aren't written in order, are they? Good catch. So 1 minus 2 is
Negative 1.
negative 1. 2.2 minus 0 is
Still just 2.2.
2.2. So that is our displacement vector.
Okay.
That's the distance, or that's our displacement vector. And if we want the length of that displacement, then we calculate the magnitude of this. And so the magnitude of that, the magnitude of delta r vector is equal to
The same thing.
the square root. Is that the same thing?
Yep.
Oh, it is the same thing. Good eye. It's equal to, once again, 2.42 meters. Okay. Now the average velocity, need a little bit of space for this one probably. The average velocity over that time is going to be the displacement over the time. So what's our displacement across this vector? 2.42. Oh, sorry, average velocity vector. So I'm sorry, we still just do this. So it's going to be negative 1, 2.2 divided by 2.
Okay.
Which is going to be the vector minus 1/2, comma, 1.1. Maybe to be consistent, write that as a decimal. Negative 0.5, and then 1.1.
It's your average velocity.
That's your average velocity vector.
Interesting.
Okay, so let's check all this and make sure we did it right. Solution. This problem involves figure 3.5, just write your answer. Part A, at t equal 2 seconds, we should have 1 meter and 2.2 meters. So 1 and 2.2. So we got that. And the rover's displacement, 2.4 when we round it to 2 significant figures.
Why you round
Okay.
it
We have 2 there, 2 there, 2 there.
But
That was
isn't
probably
just
a 0.05.
1 with the 2 at the beginning?
So I don't write all the decimal points that they actually have written in the numbers in the problem. So all the problems, like when they write 2, they write 2.0. So I'm being too lazy. So that should be a 2.0, for example. So all of them have 2 significant figures. All the numbers do. Okay. So we did that one, right? B. To find the displacement and average velocity, we express the vector v as a function of time. So let's see, v0 was 2, 0. Or sorry, r0. I don't know why I said v. r0 was 2, 0. We did that right. r2 was 1 and 2.2. 1 and 2.2. We did that one right. They just have it written out with the i's and the j's rather than just in vector notation like I have it there. And average velocity, we have negative 0.5 meters per second squared and 1.1 meters per second squared, or meters per second, I'm saying squared. So we did that one right. Was there another part to the problem? C, find the general expression for the rover's instantaneous velocity, expressive velocity at 2 seconds in component form and in terms of magnitude and direction. Okay, so we still need to do magnitude and direction for the velocity at 2 seconds. So at 2 seconds, whatever this thing, the path of this thing looks like. So we erase that arrow for a second so we don't get confused. So it's tracing out some path like this, right?
Mm-hmm.
And at this point, now I'm drawing this velocity, it has some velocity vector going that way. Something like that. Last thing we're supposed to find is the magnitude and direction of this velocity vector.
Continuing on the path.
Because it's going to be continuing down that path. So at 2 seconds, what is the magnitude and direction of our velocity vector? So our velocity vector at 2, so let's find our velocity vector at 2. That's equal to, when we plug in 2 for this, so negative 1, comma, what is that, 2.15?
Four times 75 is
4.
300.
I did 2 for some reason. 4 times 75 is 300, add the 1, so 1.3, is that right?
Yeah.
1.3. Okay, so here's our velocity vector at 2 seconds.
Okay.
Let's just draw out this vector really quick to help us see things. It goes negative 1 in the x direction, 1.3 in the y direction. So it's going to look something like that. This is 1, this is 1.3. Sorry, negative 1.
Yeah.
Okay.
That's what that vector looks like. Just redrawing it over here to help us think about it. So here's its x component, its y component. Now we need to find its direction and its magnitude. We need to find the length of the vector. The length of the vector, that's real easy. The length of the vector, the magnitude of it, is just going to be equal to the square root of 1 squared plus 1.3 squared, right?
Mm-hmm.
That comes out to whatever comes out here. Now how are we going to find the direction? We need to find the angle.
How do you find the angle?
How do you find the angle? You set up a basic right triangle, call that theta. We know this side of the triangle, we know this side of the triangle. We can figure out the angle.
Okay.
I know tangent of theta equals what?
Sine over cosine.
But what does it actually equal? Look at the picture.
Uh, 1.3 over 1.
1.3 over 1.
Negative 1.
Okay, if you're going to call that negative 1, then we need to call our tangent this angle. We call that theta.
Oh, so let's just do 1 then.
So if we call that theta, then we call this negative 1. But if we call this theta, then we need to call that 1.
I see.
Does that make sense?
Mm-hmm.
So 1.3 over 1, or in other words, theta is going to equal the arc tangent of 1.3.
Is it always the arc tangent?
If it's the arc tangent, if I'm going from tangent, it would be the arc sine if I had what sine equals here.
So when do you know if you're looking for tangent versus sine or cosine?
It doesn't matter which one you use. They all use an angle. It's just a matter of knowing what your inverse functions does. Tangent takes an angle, spits out a slope.
Yeah.
Arc tangent takes a slope, spits out an angle. Sine takes opposite over hypotenuse, or sine takes angle and spits out opposite over hypotenuse. Inverse sine, if you feed it opposite over hypotenuse, would spit out the angle. So you can find the angle using arc sine, you can find the angle using arc cosine, you can find the angle using arc tangent. It's just the two easiest numbers for me are y and x here. Because I don't know what the hypotenuse is. So I'm using tangent. And as a general rule, you use tangent with vectors because the vector gives you the x and the y.
Yeah.
So you typically use arc tangent, but there's no rule that says you have to. So when we do the arctangent of 1.3, we get 52.4 degrees, so we'll just say 52 degrees. So this is roughly 52 degrees.
And that's what we were looking for.
So the magnitude is, we can write out the magnitude here. The magnitude of the velocity vector is going to be 1 plus 1.3 squared. Oops, forgot to put my closing bracket all under the radical, which is 1.64. So this is roughly 1.64 meters per second. So you're going roughly 1.64 meters per second, and then describe this angle however you want. I'm assuming that way's north, so you can say 52 degrees north of west.
Okay.
Or you could have found this angle over here instead if you wanted, which, what's that going to be? 128? Or you said it's 128 degrees, I don't know, maybe just 128 degrees. if you
North
want to say it
of
that
east.
way. You can say north of east, but sure.
Okay.
Probably the best way to say it. Anyways, however you decide to describe that motion. So let's see how they describe the motion. So 128 degrees or 38 degrees. So they got the 52 degrees here. They calculate this as 128 degrees, and then they calculate this angle right here is then going to be 38 degrees. And then they say 38 degrees west of north.
West and north.
But our answer obviously was just as out.
Okay.
Doesn't matter which one you get. All equally valid. So there's an example using those vectors and trying to get comfortable with those vectors.
Okay.
Okay? So we'll give you the rest of class for homework. Sorry about the cut in the lecture. And then we'll continue from there next week. Strongly recommend looking over the section.